the derivatives we've done so far have been derivatives with respect to x. So we would have dy dx, again that just means the derivative of y with respect to x. But in our new unit, we'll be taking derivatives with respect to t. And once we get into our actual applications, t is going to be time. So anytime we take the derivative of a variable other than t, we need to apply that chain rule. So my first question would become the following.
On the panels, please call extension 1510.
Again, anytime we take the derivative of a variable other than t, we need to apply that chain rule. The derivative of x with respect to t, the derivative of y with respect to t. And really it's as easy as rewriting that each time, applying that chain rule, since we're now taking derivatives with respect to t. The second one is just a nice question because it's practicing our product rule and our chain rule at the same time. So our last unit, or our last section in this unit is 2.6, and we're going to be using our implicit differentiation skills and differentiate usually with respect to t. So in this first example, it says, suppose x and y are both differentiable functions of t. Really, that statement is just saying take the derivative with respect to t like we just did. And they give us an equation where they're related by y equals x squared plus 3. The rest of the information we're going to plug in after we take our derivative. Because again, those numbers like x equals 1 and dx dt equals 2, those are constants. If we plug those in before differentiating, any constant is 0 when I differentiate. So always first take the derivative. Once we have our related rate equation, now substitute in the information that we have so we could find out what that dy dt is. Example 2. When water is drained out of a conical tank, the volume V and the radius r and the height h of the water level are all functions of time t. Again, it's telling us when we want to obtain this related rate equation, we're going to differentiate with respect to t. We want to see how all those variables are changing as t changes. I wouldn't give you this equation, or I wouldn't ask you to memorize this equation. I'd probably just give you the volume. But try differentiating. So again, differentiate each piece separately. This becomes dv dt. Then I have my product rule over here. So first I rewrote the pi over 3 times r squared, and I took the derivative of h, which is just 1 and dh dt because my chain rule. And then I did the other term. Multiply by 2, drop the exponent by 1, dr dt, because I just took the derivative of r, and rewrite the h. So question 3 finally puts all these concepts into a word problem. So a pebble is dropped into a calm pond, causing ripples in the form of concentric circles. The radius r of the outer ripple is increasing at a constant rate of 1 foot per second. When the radius is 4 feet, at what rate is the total area of the disturbed water changing? The first step in all these equations is first figure out, all right, well, what's the equation that's relating all these variables? You have area, you have the radius. In this example, well, we just want the area of a circle. They told us they were forming concentric circles. And again, if we're dealing with rates, that's always our key word for take a derivative. Now take the derivative so we could see what that change in the area is, that dA dt. Now that we have our related rate equation, how the area changes with respect to the radius, if I look at when the radius is 4 feet, well, that's what I'm going to plug in for r. And then they also tell me that the radius is increasing at a constant rate of 1 foot per second. That 1 foot per second, that's my dr dt, right? That's the radius, that's the rate it's changing at. So plug in those two numbers to get your answer. Lastly, our question is, air is being pumped into a spherical balloon at a rate of 4.5 cubic feet per minute. Find the rate of change of the radius when the radius is 2 feet. So the first step each time, well, what equation is actually relating all of those variables? It says the volume of a spherical balloon. That's the volume of a sphere, and we use that in our very first unit in a question on the intermediate value theorem, I believe. I don't actually expect you to remember that. It's great if you do, but I'll probably give you that on a test if this question appears. So anyways, that's my equation that relates my volume and my radius, and now we're going to differentiate again with respect to t. I almost forgot my chain rule there. Do not forget to multiply by dr dt. So that's our related rate equation. And now go in and see what are the additional information that they gave me. They want me to find the rate of change of the radius. Well, the rate of change of the radius is that dr dt, so I'm not going to plug in anything there. They must have given me information that is the other two variables. R, well, they did right here when the radius is 2 feet, so I'm going to plug in the 2 over here to r. And dv dt, well, look what they gave me. Air is being pumped into a spherical balloon at a rate of 4.5. Air being pumped into the sphere. That's my change in volume, right? dv dt is 4.5. I'll put it in as 9/2, so we don't need to use our calculator. So 9 over 32 pi, if we don't have our calculator, is the rate of change when that radius is 2. These are just the steps right from page 150. In other questions, when we start to get to more complicated ones, it's helpful to draw a picture always first and identify what pieces of information they're giving you. And then step 2 is create your equation, but always differentiate first. Don't start substituting in information before you differentiate, because again, the derivative of a constant is 0 and you'll just ruin everything. Here is your classwork and your homework. And on the last slide that I'll post, I also give you the answers to the even homework so that you can check those as well. All right. I missed you guys today. See you tomorrow.